Okay, welcome everyone to the Oxford seminar. This week we're hearing from Q, who will be telling us about enriched categories applied to qualia spaces.
Thank you for that introduction, Jason. Before we get started, I'd just like to thank some people. So firstly, I'd like to thank Kobe Kremnitzer, who was my supervisor for this third-year project. He was incredible, and I couldn't ask for a better supervisor for this. I'd also like to thank the Association for Mathematical Consciousness Science, partly for inspiring this work, and I'd like to thank Topos for providing me the chance to discuss this. Okay, so the basic gist is there's this paper. So in 2021, there were three researchers, Tsuchiya, Phillips, and Saigo, from now I'll call them the authors, who introduced enriched category theory to model a notion called similarity judgments in qualia spaces, where qualia is a quality or property as perceived or experienced by a person. So, for example, how you taste lemon, how you feel pain, how you see the color red. And after reading this paper, there were a variety of concepts and also a lot of questions that came from them. Particularly, of course, they introduced enriched categories to describe similarity judgments, which itself is a very massive field, actually, in consciousness, or at least sort of psychology. They also describe advantages of this enriched categorical approach over other standard models. And not just in this paper, but throughout their work, they advocate for a certain categorical approach, which I'll call the Yoneda-based approach, over other, say, structural or relational theories of qualia. And as to the questions, well, there's a variety. So from the paper itself, they leave a bunch of open questions towards the end, including what kind of relations, including similarity, can form an enriched category, which I thought was a good enough question to do a third-year research project on. But there's also other questions that pertain to the general approach. One is, does it actually work, what they describe? We'll get into that a bit later. And then also, what are some possible other applications of enriched category theory to this domain? So here's what we're going to be talking about. We're going to motivate the scenario with monodal categories to enrich categories. We'll talk about what the author's quote-unquote result is and their reasoning for their approach. We'll talk about certain developments that I've made. And then we'll end with conclusions, open questions, but then also a general discussion about the role of category theory when it comes to consciousness science. Now, I am aware that there may be neuroscientists and philosophers who will be viewing this talk as well. So to preface, probably you only need to know what a category is. And then aside from that, I'll try and explain as best as I can the rest of the talk, but there will be references at the end if you're interested. So here's the idea. So suppose that we have a bunch of participants who rate the similarity between colors. So here's an example study where you have some finite set of colors and you ask participants, okay, how similar is X compared to Y? Here, this is known as a matrix of similarity values, 0 being no similarity at all, 1 being exact similarity, hence why along the diagonal it's entirely ones, right? Funnily enough, actually, it is an assumption that X being similar to Y is the same as Y being similar to X, hence why it's a symmetric matrix. But actually, there is evidence to suggest actually that people don't see it as a symmetric relation, which is interesting. And the general question is, given a collection of qualia and continuous degrees of similarity, in this case from 0 to 1, as morphisms, can this become a category? So this is the general question that they ask. And if you let's suppose that maybe we could. So we try and model it with sort of an ordinary category. So given some similarity scale, the authors they define this notion of the threshold of similarity. So they say, okay, let's say that they are similar if and only if their similarity value is bigger than 0.5, right? Okay, and we define a morphism if this is the case. But in this case, then, well, given this matrix, for example, you see that green is similar to turquoise is similar to blue, but green is not similar to blue. And so there seems to be a breaking of a composition, let's say. So the authors suggest that similarity as morphisms does not make a category, so there's no composition, right? Okay, but what's the issue here? Well, the issue is that this threshold of similarity is rather arbitrary, right? You can make it 2.5, you can also make it any other number. There seems to be something missing when you just instantiate this threshold of similarity. And that's simply because similarity is just too binary to consider, right? We need this notion of gradations. We had our data as a scale. And so we would like to describe some type of scale as a morphism, instead of just it is or it is not a similarity. That is, we need our morphisms to live in some structure that has more data than just a set. So what should this object be? Category theorists, this is quite a natural structure. It's called a monodal category, right? So you just have a category, but you also have this notion of a monodal product, and you also have a monodal unit, and they satisfy some associativity and unity axioms that I won't get into right now. And so in their question, in their paper, they bring in monodal categories to model the notion of, well, similarity, but then really strangely enough in their paper, they then ask about dissimilarity. So they give an example. So suppose that we had a bunch of objects from 0 to infinity, excluding infinity. We describe morphisms as x goes to y, if x is bigger than or equal to y. Monodal products such as addition and composition is clear. And then the monodal unit as 0. In fact, actually, this is just a metric space, excluding the symmetry condition. And so suppose that we had a qualia category, Q, which could be our set of objects, then we can take, say, the distance from x to y, y to z as objects inside of 0 to infinity. Then what does this composition law look like? Well, this manifests as the triangle inequality, right? And the identity map would also correspond to the distance from an object to itself being 0, right? And so if we did this for every morphism between qualia, then we could say that we have enriched our qualia category with this dissimilarity category here, D. And this is actually just what enriched categories are. So we have a category, and between two objects, we just describe a Hom object, where this Hom object, instead of just being a set, it now resides inside of some more structured category V, which is monodal. And then for our morphism, instead of it just being direct, we have a composition morphism here, right? And also a identity morphism as well. So the key thing here is that our Hom object isn't just a set now. Well, it could be if you take V to be the category of sets, but it could also be something else, right? And depending on your choice of V, you'll add certain extra structure to your set. So what's the key result here? So the authors show that, quote unquote, a collection of color qualia with dissimilarity as morphisms qualify as an enriched category. Okay, sure. But why is this useful? Why do you care about this? So the reason they do this is, and this is something that you see a lot in their actual papers, they push for a certain categorical approach to consciousness. And it can be characterized in the first statement here. Finally, we discuss the fundamental motivation of our enriched category framework. That is the consequence of the Yoneda lemma to characterize the quale, which is just a single qualia, as its relationship to all other qualia. And they even provide a way for quote-unquote researchers to use this, which is make the category explicit, aka specify objects, relations, and how those relations compose. And in another paper of theirs in 2021, which is like a relational approach to consciousness, I think, they say the essence of the color experiences resides in relations with other colors. So it's a very structuralist approach. Now, for a lot of category theorists, they might see this and say, this isn't exactly what we're saying. There are many critiques of this categorical approach to qualia anyway. So, for example, there was a paper entitled like IIT and structuralist approaches in general and why they don't work. So you can attack this from basically saying that structuralism doesn't work for consciousness science. On the more mathematical side of things, some have said that this isn't how Yoneda's lemma is used. That is, there are issues with this characterization of Yoneda's lemma. We'll get into that later. But the main idea for this research project of mine was basically assume that they are correct. So assume that this is true, like you can do this. Can you, in fact, identify an object up to isomorphism, right, via these relations? And I show that this isn't possible, aka that there is a contradiction within their own framework, so they should probably change a bit. So here are the key things. So first of all, it was quite peculiar that they switched from thinking about similarity to dissimilarity categories in the paper. So I'm just going to address that you can make similarity categories. In fact, there's many different ones of these, different models of this. And it might be enlightening just in general to consider these different models and how they fit in our experimentation. The other one is, quote unquote, how can we use Yoneda's lemma to classify qualia in terms of their relations? And in general, just is, and this is a well-known fact, but we'll go through it together, that this isn't always true. That is actually for two-ary relations. This is only true when it's reflexive and transitive. And if you look at all of their examples that they provide in their papers, they are all reflexive and transitive relations. And then the third one just comes directly from their paper. What kind of relations, including similarity, can form an enriched category? And this, though the answer might seem quite easy for maybe a trained category theorist, it might be enlightening just to see what it looks like for neuroscientists and philosophers. And it's actually a bit more complicated. Even the notion of what it means for a relation to form a category is a bit strange. So yeah. And then finally, we'll talk about another application of enriched category theory, which is simply that enriched quivers may act as data structures for qualia observations. Assuming that these qualia observations are not actually, they don't necessarily need to form a category, enriched quivers can still work. And so maybe there's something to do with that. And we'll also discuss just in general the role of category theory at the end. Okay, so the first general gist is, given a dissimilarity category, and given a similarity category as well, well, what does it mean? What do these two concepts mean? Similarity and dissimilarity. Under a certain approach, they are just opposites of each other. And so in general, if you just have a dissimilarity category, you can just take the opposite of it to make a similarity category. Easy, right? And so both of these can enrich a qualia category. Also, I should probably preface, we are assuming the qualia category exists for this work, except I'll also later critique that it's not necessarily true. Actually, there are certain philosophies that say actually there is a distinction between similarity and dissimilarity. That isn't just that they're opposites. So that would actually be interesting to consider here. So we have considered maybe dissimilarity as a metric space, but like, are there any others? And particularly because our example only did from 0 to 1. So maybe we would like some type of categories in that way. And actually there are. So there's this notion called a T-norm, which comes in fuzzy logic quite often. And actually it's quite nice that every T-norm, whether it's minimum, product, and drastic or whatever, each of these provide dissimilarity categories. And so you can have from every T-norm a model of dissimilarity or similarity judgments. Okay? And very nicely, then, it might be useful then to consider what T-norm might represent, quote unquote, similarity or dissimilarity when it comes to qualia observations in general. So that's just a very small one. So the second question was to do with their approach, right, to consciousness. And to understand that, we need to understand what the Yoneda lemma is. Now, this is the actual Yoneda lemma. For the neuroscientists and philosophers, I'm really sorry, but we're going to have to understand this. So practically saying, it says that if you have a category and it is locally small, aka the collection of morphisms between objects is a set, right? And then you have this functor category C op to set, which is the functor category, so it's just functors from C op to set. and then you have this presheaf, and then there's this canonical isomorphism between the Hom set of presheaf homomorphisms from the representative presheaf, your C to X, and the value of X at C. So this is the actual Yoneda's lemma. Very interestingly enough, and there's a reason for this that I'll get onto when we go through the discussion, the authors of that paper actually describe a corollary of Yoneda's lemma as the Yoneda lemma, which is this one, which is that if C is a locally small category, then two objects A and B are isomorphic if and only if the morphisms going into each object is isomorphic naturally. So this is what they identify as being the useful Yoneda lemma. For the intuition behind it, here's a quote from N-ary, which is a really nice website for category theory. You should definitely look into it. Probes by objects of C are sufficient to distinguish objects of C. So two objects of C are the same, well, up to isomorphism, if they have the same probes by other objects of C. So philosophically speaking, this just means that an object is quote-unquote defined by its morphisms to all other objects, including itself, or that an object is defined by its relation. And this is a very structuralist approach, right? Now, why is this useful? The reason why this is useful is because try and define the experience of seeing red just by itself without mentioning really any other colors or things like that. It's incredibly difficult to do. In comparison, if you try and describe how red is in comparison to blue, right? So how cold red feels compared to blue, right? This is far more tractable of a problem. And so the general idea, at least that the authors would like, is that we can use this Yoneda's lemma to basically replace the problem of identifying quale or identifying qualia with identifying the relationships between qualia. That's what they want, right? And so does it work? So they want to use that. So how can we describe this notion of relations that they have? Typically, a relation is just a subset of S squared, where we have a set S. But actually, the philosophical definition of a relation allows for N-ary relations, aka relations that relate N objects together, right? So we need to allow this in our framework, basically. Given that we're using category theory, it kind of makes sense to describe a relation or an N-ary relation as a category. So we have for a set of objects S, we're going to assume that S is a set. We'll get into if it's a class later. An N-ary relation R on S is simply a mapping, or simply a functor, sorry, from S to the N to truth, where S to the N is a discrete category, and truth is the category, I didn't explicate it here, but it's the category where you have false and true, right? And there's identity morphisms, but there's also a morphism from false to true. It's also monoidal if you take true as the identity. And so like true is true, true is false is false, yeah, and false is false. Okay, nice. So this is an example. You can go through it yourself. It's just saying that you have two area relations. You can also have three area relations. We can imagine then a morphism as an instance of a two area relation, at least as I can understand from their work. And given a two area relation R, we can then construct a quiver, which I'll denote as QR, which is just a directed graph whose objects are in S, and there's a directed edge from X to Y if X relates to Y, right? Quite nicely, there's a very simple, you can construct this entirely, that there's just this correspondence between two area relations R and thin quivers. So we can just deal with thin quivers, practically speaking, when we're going to investigate this. So what do they want to do? So the authors, they want to use Yoneda's lemma to classify an object by its relations. This is what they want to do. These relations with other objects are morphisms. They don't state this necessarily, but because we're talking in terms of, at least with the category theory that they're dealing with morphisms as the relations. So instances of two area relations. But the thing is that philosophically speaking, the relations are higher, can have higher arity. and they don't necessarily need to form a composition law, as they might imply or suggest. And so to see if Yoneda's lemma can be applied for this arbitrary N-ary relation, as is claimed, we need to answer when this N-ary relation can make the quiver that it has into a category. In general, though, actually, I'm actually uncertain whether for n bigger than 2, it necessarily makes a quiver. It might make like a multi-quiver or something. We'll get into that in a bit, right? And the general idea is that they want to, if you have a quiver and you can show that it's a category, then you can, quote unquote, use your Yoneda's lemma to then do this classification process of an object by its relations. aka, you can preserve the information of the relation by viewing it as a category. So that's our task for today, right? And in particular, what would be really nice is if you can provide some non-trivial characterization of R, right? Instead of just check that it's a category, right? So this is the task. I'd like to thank Tim Hosgood for this perspective. So there's two ways to go about this problem. And one of them is by considering profunctors and morphisms in this truth category. And just kind of checking it explicitly. I'd like to thank Tim for this. I had another approach that was a bit different and ended up not being correct, let's say. But actually, there's two perspectives, together they sort of complete the answer entirely. And I'd like to thank Tim for this approach. So yeah. So for now, let's just restrict it to area relations, right? So a category C is enriched over truth. It has the same objects, and the whole object, remember, it resides inside of truth, right? Because that is our monodal category that we're enriching over. And so that can be either true or false, right? We can then consider, say, a morphism from C to C dash as being whether C relates to C dash, right? Then to get composition morphisms, we just compose them together, right? And what we notice is that if this was actually a category, then we would require the relation to be transitive. And we would also require that one should actually be a T or whatever. It should always be reflexive as well. That is, we require R to be transitive and a reflexive relation, aka preorder. And conversely, preorders give rise to truth categories. So already immediately, just from considering this, we can already tell in the 2-ary case that, well, not every relation works to be a category, right? Because it has to be reflexive and transitive. So you can't just have any arbitrary collection, it has to be these two. For the general case, this is like actually a lot more difficult. You can view it as a profunctor from S, a truth value profunctor, I should say. Yeah, so a profunctor is just a functor from S to the n minus 1 times S to truth. And because truth is symmetric nodal close and complete, we can then perform this currying operation here. Now, actually, describing what R is and giving a non-trivial description of R is just actually really difficult to do here in general. So I haven't had enough time to do it, but you might require the use of multi-categories, or I think there's a thing called enriched categories. When n is even, though, you can split it to S to the m to S to the m, and so you can reduce the problem down to just considering odd values of n, excluding 1, right? So that's the basic idea. But then there's another perspective here, and I would like to thank Kobe for this. Also, you know, I'd like to thank Jose as well. So, like, I should probably say, so last week I had to really understand the content here, and I was learning under Jose and Kobe the notion of like monads and T algebras and analytical categories, and actually they just fit perfectly here. So yeah, I thank the two of them for this approach. So another way to answer this question is to consider when a quiver arising from a relation makes a category, aka if we need additional morphisms for it, right? you can let's restrict back to two-area relations. You can again construct this theorem, right? The corresponding thin quiver can be seen as a thin category, respecting the structure enclosed by R. So if you have a reflexive transitive relation, you can view it as a category. The quiver can be viewed as a category. As to what it means to view the quiver as a category, we'll get into later. But for now, we'll take this for granted. And then viewing, by quote unquote using Yoneda's lemma, we can then obtain all the information about objects inside of S with respect to the relation, right? Which is what we'd like to do. So what about for an arbitrary relation? How can we do this? Can we make an arbitrary relation a category? Can we force this in? Well, there is actually just one construction that's quite nice. So one way is that we just make the objects fixed, so we keep the objects the same, but now our morphisms are paths between objects, where a path is just a finite sequence of morphisms connecting one vertex to another. This defines the notion of a free category of a quiver, and we can describe this construction as a functor, right? Which is a free functor, and it's the free functor from the category of quivers to the category of, well, small categories, right? So suppose we do this, we take an arbitrary relation, and then we make from this relation, or the underlying quiver of it, the free category. How unique is it? Well, by a thing called the universal property of free categories, we know that this is unique up to isomorphism, right? So we have free category, free functor from quiv to cat, and likewise we have a forgetful functor from cat to quiv, such that f is left adjoint to u, right? Is there another way to construct a category given a random quiver? Well, up to isomorphism, no, from this relation. And so given a relation and its underlying quiver, we can construct a unique category. But the thing is that this free functor is not injective on objects. And so sort of immediately here, we can sort of see, you're going to lose, quote unquote, lose some type of information when we're applying this free functor to just an arbitrary relation. AKA, you can't, quote unquote, use Yoneda's lemma on the free category that's produced to get back your information about the quiver, basically. But actually, this isn't immediately applicable to our quiver, just because we might add additional arrows, right? When we do this free construction here. And so here's the idea. How can we resolve this? Well, given this adjunction, we can construct this monad, right? Which is just taking our forgetful functor and our free functor, composing them together to get this functor, let's say t, from quivers to quivers. And here we have these two unit and multiplication natural transformations. You can just interpret these as eta embedding every arrow or morphism as a path of length 1, and you concatenate the path of paths into a path. And then likewise, we can then describe this notion of a T algebra, which is just a quiver Q, equipped with this map from TQ to Q in quiver, such that we have sort of identity and also something that is analogous to associativity. And by considering this, by considering what's required of T algebras and T algebra morphisms, here we can observe that T algebras correspond exactly to small categories, and T algebra morphisms correspond exactly to functors. So if we collect all the T algebras together and the T algebra morphisms together, we construct this category called the Eilenberg-Wall category of quiver, of T with respect to quiver, and this is isomorphic to cat, right? Okay, that's interesting, but so what? How can we use this to identify when a relation, quote unquote, can make a category? Well, what we can do is just think, what we require is, let's say this A, if we have a quiver QR, we require this sort of map from TQR to QR, right? What does it do? Well, T itself might add a number of arrows to the quiver, right, to restore composition or whatever have you, right? So maybe one way of saying that a quiver can already be seen as a category is if you don't need to add any more arrows, practically speaking. And that just means that there exists this A, and we can make a T algebra for it, because then that makes it correspond to a category. For thin quivers, this just means that we require the existence of identity arrows, and that every composite path already has an existing arrow inside of it. And this just corresponds exactly with reflexivity and transitivity again. Okay, so we have these two perspectives. One is with profunctors and morphisms, where you can just identify conditions for the relation quite easily based on the enriched category B. And the other one is through monads and algebras, which makes it sort of easier to discern when a given relation does make a category without actually considering the actual conditions that are placed on the relation itself. Okay. So already we've already, in terms of what Tsuchiya is trying to say, we could already see just by considering two area relations that, well, you can't apply what they wanted. You can't do that, right? So hopefully that's convincing enough for them to maybe not do what they're doing. But then there's another question that they pose, which is what kinds of relations can form enriched categories? This is a more, let's say, substantial question. We've already hinted at the fact that we can consider maybe truth, or the monoidal category of truth, as enriching our relation. And so let's do this in general. So we can, given a category V, we can describe this V relation or N-ary V relation analogously. And given a quiver, we can also describe, we can describe a V quiver or a quiver enriched V quite analogously to how we consider enriched categories. So bunch of objects, and we have a V-bounding functor taking Hom sets between two objects into the category V. And again, we'd like to determine which enriched relations lead to enriched categories. Let's go ahead and restrict again to enriched two-area relations. And again, we can get this correspondence quite nicely between two-area V relations and thin V quivers. So again, we can just consider thin V quivers naturally. Okay. Now this is the goofy part. So basically speaking, the really nice thing with considering just truth is that the construction is quite clear on how to make the quiver into a category. But the thing is that doing for just a general enriched quiver or for a general enriching category is just a bit different, let's say. And we have to use this analogous theorem, which comes from Wolff's paper VCat and VGraph. VGraph is the same as VQuiv, I think. Here it just says let V be a co-complete symmetric normal closed category. And then there exists this free functor and the forgettable functor between VQuiv and VCat. As to the actual construction of this functor, I'll have to relay it to the paper itself. We can intuit what it means again. So like we have this, we can construct again a monad. We have this eta which embeds enriched arrows as enriched paths, length 1, and mu concatenates a path or an enriched path of enriched paths as an enriched path itself. The reason why you require it to be co-complete, actually, I think in the original paper, it just needs it to have co-products. And the reason why you need co-products is just so you can, quote-unquote, add these enrichments along the paths together, because here, the enriched path of enriched paths, the enrichment of each path might be different each time. So you need some way to sum them all up together, and that's what the co-product is there for. So yeah, so we can use this again. So again, when our thin V quivers V categories, we can again construct the T algebra. We can again consider for V, which is co-complete symmetric monoidal closed. We can see that T algebras correspond exactly to small V categories, and T algebra morphisms are V functors. I think think this is shown in Wolf's original paper. And then again, we can say that maybe a V-quiv QR is seen as a category when we can find this map, or sorry, this map A from TQR to QR, such that QRA is a T algebra. Okay. Again, we're only considering thin V-quivers, so we just need to show that there are identity morphisms and that there already exists a morphism that allows for composition to occur. Okay. The thing is, though, is that this characterization, this description, depends on V, right? So let's just go ahead and see what these might look like. So, given a Benabou, I think that's how you say it, right? Benabou, Benabou cosmos V, which is just bicomplete symmetric mononucleoid category, I think. Basically, it allows you to do this. What condition is placed on R? Well, let's suppose that our enriching category was a set. Then, after doing your calculations, you can just see that QR is a category if and only if your collection of relations has identity elements and associative composition. This doesn't actually say much. This is almost precisely what you need, really. And really, the best thing you can do is just check, right? There's not much else that you can really gather rather than just checking here. Let's take some other examples. So if we imagined instead the category of vector spaces over a field K, again, our quiver is a category if and only if this family of relations becomes a K-linear category. But again, you just need to check, right? And finally, let's suppose that we considered this. I think this is the Levier generalized metric space. Maybe not generalized, but the Levier metric space. Yeah. And then we can characterize it as a quiver is a category when R, the relation, acts, quote unquote, or is a Levier metric space. So from these observations, so I haven't tested every Benabou cosmos. I don't know if there's a finite number of this classification, but it seems that given a relation R, sort of the best thing we can do is simply just to check if R itself, well, is a category, and if it just makes it work, which isn't really helpful for our observation. This might highlight really just the fact that the truth category as an enrichment is quote unquote rather special. Not actually because there's anything intrinsically special with it, but actually just because we've defined what it means to be an identity and associative there, which is just reflexive and transitive over that. So we don't have analogous words to make this classification nice and easy, let's say. In general, actually, so I'd like to just know, actually, wait, no, we'll get into that later when we get into open questions. But Tim suggested that actually there's probably a way of characterizing R through the use of presentations of categories, which I didn't have enough time to delve into, unfortunately. But I'll leave that as an exercise for the listener. So the general idea, at least sort of the motivation for this, is supposing that you had a data set, right? Can you make it into a category? We have seen that we cannot generally make it, we can't force it into a category. And if we did force it into a category, then you might add additional arrows, you might add additional information that you wouldn't technically have gotten from the quiver itself. But here's maybe one example of maybe how we could use it. So take an observer P and some Benabou cosmos V, right? We can define a finite set of objects, for example, certain qualia. We can ask P a bunch of questions, each relating objects in S to all others. So like how cold X is compared to Y, how angry X is compared to Y. And we can like force P to choose from an element of the Benabou cosmos here. Each question will provide this V relation based on the question index. And this corresponds with the V quiver. And then once data collection is done, we can construct this product quiver, which might be why we need it to complete, maybe. And then we can view this quiver, this product quiver, as being just a nice data structure that we don't affect the data with. So this is just a data structure by itself, which captures piece perspective without any real external requirements aside from the choice of V, right? So we're not affecting it. We're not forcing it to be category or anything. We're just letting it be. And then if you want to do experimentation, you can. This is just a data set, really. But one, you might not like the fact that we have to choose our Venn cosmos first, right? Some questions, like, I don't know, how angry is X compared to Y? It doesn't make sense to use a number from 0 to infinity. And actually, I must presume that this might be like another question to consider, which is just given just a set of entries, aside from the discrete category, can you make other interesting category stuff on it? Can you make it into a nice category that we can then use for this? I would probably say no, but I don't know. I don't know myself. So yeah. So in general, again, we'll just go through it quickly. Are there other similarity models? Are there other dissimilarity models? Yeah, there's actually loads. You can find them out. Can we use quote unquote Yoneda's lemma to classify qualia? Not always, only for reflexive and transitive relations, two-area relations. What kinds of relations form enriched categories? Well, to put it quite, let's say, just abstractly, for two-area relations, those which allow for T algebras to occur. And then again, we have this application of enriched quivers as data structures. So I want to, yeah, so like let's go through some open questions here. So just extending these to N-ary relations, again, we might require the use of enriched multi-categories. I personally, so like me and Tim, we had considered like the currying procedure might be nice, but I don't know. I don't know how to extend the current methods to N-ary relations. I just don't know what multi-category is. So that might be interesting to consider. And then using alternative V for data structures, where this V is a Bonabu cosmos, right? It would be actually interesting just for general experimentation whether there is any use in considering a data structure, or sorry, considering sort of the menu of choices other than say numbers or integers or things like that. What would it mean for someone to select a vector space as an option on a menu? Like I don't know myself. It might correspond to something nice. I don't know. And then finally, this characterization of a relation R to make its quiver. Well, I'm assuming R makes a quiver. Actually, for higher airy relations, this might not work. R might make something a bit more complicated than a quiver, probably. But in general, it might be useful to consider how to write this or express this in terms of profunctors and morphisms. Tim Hosgood again referred to this idea of a quiver representing a category. It might fit here, it might not. So here is the issue with categorical consciousness so far. I can only point out sort of three things. So the first one, again, resides in their approach. So this presentation, I've assumed their worldview. I've assumed that you can, quote unquote, use Yoneda's lemma like this to preserve information, to classify objects. But is this actually what we mean by Yoneda's lemma? Tim mentioned something quite nice, and actually, it's something that's pointed out here, and it's a very small linguistic thing. The essence of an object resides in relations with other objects. The key missing point in that quote, or in that general sentiment, is that the other objects include the object itself. So you cannot avoid observing or understanding how an object interacts or is by observing how it interacts with other objects. Because to apply Yoneda's lemma, you have to see how it interacts with itself, right? Which is under a certain philosophy, basically just understanding the object itself. Okay? So you can't avoid investigating the original object. Maybe one way you can do it is just by forcing this identity morphism, but that doesn't really say anything. So yeah. The other one is the sacrifice of mathematical rigor. And I'm not claiming that they aren't mathematically rigorous. What I am claiming, however, is that in the general consciousness community, there seems to be a understanding, at least among the mathematicians and the computer scientists, that for the more rigorous proofs, there might not be a journal for us. The reason why is that you have your neuroscience, your philosophy, and your math journals. Neuroscience and philosophy have their respective consciousness journals, but for mathematicians, we don't necessarily have that. And so when we want to publish, say, research, which applies some maybe more abstract mathematical techniques or what have you, of theory, to consciousness, we might have to reduce the, let's say, the quote unquote rigor of the paper and appeal to intuition, right? And this is so that we can hit the neuroscientists and the philosophers. This is totally fine. I don't mind. I think it's actually a good thing for us to apply our intuitions. However, we should really be grounding it in some type of rigor. And actually, this came up in a Bamberg conference last year. So I went to the Models of Consciousness conference last year in Bamberg, and this is known. And Johannes Kleiner, who is a fellow mathematical consciousness scientist, he is working on developing starting a mathematical consciousness journal. So hopefully this, trade-off of rigor versus intuition, we can resolve that together. But then finally, here's another one. Is qualia a category? This is an underlying assumption of all of their work, the author's work, I would say. In fact, in 2025, this year, they have started a qualia periodic table to try and classify qualia in terms of the relations. And it's assuming that qualia can be seen as a category. Now, in Robert Predner's paper, I think it's called Category Theory Beyond the Consciousness Project, I think, he has found that it might be possible to make qualia become a category, right? To have this category of qualia, but is this useful? Is this necessary? You might appeal to some philosophy like structuralism, whatever. However, the real question is how can qualia compose? Can qualia compose? In certain philosophies, qualia do not compose. They are simply there. They are simply a thing. And the moment you compose it, it makes it is itself a new qualia that you can't decompose into itself, right? So maybe you can appeal to philosophy for that. But this is sort of maybe one underlying issue that we have with this approach itself. So then what is the role of category theory? This will be a few final minutes. So there's sort of three things which I think sort of characterize at least what category theory kind of give to consciousness science. One is the Tsuchiya Saigo approach, which is this characterizing qualia and finding a category of consciousness. In fact, actually, in the 2024 paper, if you search up category theory, consciousness, universal property, Tsuchiya characterizes consciousness as a universal property. Is this true? Maybe it is. I don't know. But that's possibly one role. Another one is explicating structural properties of consciousness theories. So you might well know that there are a variety of consciousness theories that are battening it out. So there's integrated information theory, there's global neuronal workspace theory, there's a whole bunch of them. And actually, one thing that's quite useful is that category theory can observe, or maybe not observe, but we can use category theory to observe, say, some structural properties of these theories and how they describe things. And actually, Tsuchiya does do this in 2016. So yeah. And then the final one, and I think this is actually really interesting because I have never seen it actually like talked about. So in the 1980s, there was I think a neuroscientist and a mathematician working together, and they basically discovered or founded this field of memory evolutive systems, which is practically using category theory to model, I think, how memories work, or how maybe not how memories work, but in general, just using it and applying it to neuroscience. And in general, this might be a good thing as well, modeling philosophical or neuroscientific theories via category theory. So yeah, these are three possible roles. There might be more roles to come into the future. This is a very young field, and it's a very dynamic one as well. So yeah, it's safe to say, even though category theory might not be able to, be used for finding categories of consciousness, it could be used elsewhere in consciousness science. So yeah, do you have any questions?
Questions? I guess I do. I'm sort of interested. So that I guess the concrete example we've got of like actually using some Cosmos V to describe this as a V category is, I guess, essentially looks like a metric space or maybe some other similarity.
Yeah.
Cosmos. And I guess there are nice things that are true when you're working in a Cosmos, which is a poset categorical, right? Like you can check whether a quiver has, if it admits a V category structure, it's essentially unique for its, if V is not thin, then there are lots of different composition rules. Are there non-poset Vs that people are actually using to try and describe categories of Qualia?
I actually don't think so. So like I must wonder like whether, because like it would be useful to observe whether a certain qualia can be structured not as a poset but instead of other things. In general though, through my like look into the literature, I don't think so. Most, when it comes to at least color similarity, most of them they try and map it. They realize that metric space does not work. Actually, this is one thing that motivates the use of enriched category here, which is that, well, metric spaces don't work. The notion of symmetry doesn't work. The notion of transitivity, actually, experimentally speaking, doesn't work.
Sorry. Oh, right.
So as in terms of like qualia, as in like qualia observations.
Right. Like that matrix is good at the top. Are you saying actually, if you
Sometimes,
people, you
yeah, for some people, it's actually like not symmetric, that matrix, which is really interesting. So sort of there are some models of color similarity, like some of them I think use, I think a hyperbolic space, I think, or I've forgotten the terms, but they use other mathematical objects.
The point to like modify the monodal product so that you do get this like triangle.
It's actually really there's a notion called a kernel reconstruction approach, which I don't agree with, which is that, so I think, so there is this model, I think it's the hyperbolic one, and given this matrix of values, you can perform a function on it to make it fit the model. But I don't like that, because it doesn't really make sense to fit the data to the model when you should be fitting the model to the data. So
thanks for the talk. So when I was an undergrad, I also did some similarity research in psychology.
Okay.
One thing I remember from that is that similarity is not reflexive, it's not symmetric, it's not transitive, but it gets worse, right? If you take your subjects and you split them into two groups, and in one group you ask them first, how similar is X to Y, and how similar is X to Z? In the second group, you ask, how similar is X to Z? How similar is X to Y? Different answers. In other words, the ratings of the observations of similarity do not compute for in other words, it depends on how you test the order in which you test people.
Yeah.
Where, in other words, the similarity relations that people give to experiences, which are used here, it seems that they I get a little confused to say complete qualia and experience, is that you test the similarity of experiences.
No, yeah.
And in particular, the experiment we ran was a one that showed that if you have, people discriminate along a certain, axis, they will rate things along that are more similar along that axis as more similar than if they had rated along a different axis.
Yeah.
So, like, in other words, just having people do a discrimination task, which makes similarities and differences more salient, changes that.
Yeah.
So I wonder if there is a role here. One of the assumptions I see making you, so you rightly pointed out that we can't really assume it's a category because it's not reflexive, it's not transitive. It's not only not symmetric, but it's not reflexive or transitive. However, there's a sort of meta level assumption, which is that the V you've always assumed was a symmetric normal.
Yeah.
And that symmetry appears in the law of transitivity as saying that if A is similar to B and B is similar to C, then A is similar to C. That and is assumed to be symmetric. However, because the way if you actually ask someone how similar A is to B and how similar B is to C, you would get a different answer than if you asked how similar B is to C and then you asked how similar A is to B. So I wonder if you've considered also using non-symmetric B.
Yeah, low-key, I have not actually considered that. I did know that they there is a temporal dimension depending on the judgments that people make. I didn't know it was that severe though.
It sounds like it should maybe be bridged up with something like random variables.
Ooh.
Maybe you just described.
Yeah.
We can only give like a statistical description of how you did about the experience.
But that would be like if it was just randomly, like if the error was random rather than systematic based on the order you ask the questions.
Yeah. It's actually so like pointing out this quote unquote experiment here. Sorry. Like, oh my god. Yeah, this is ages away. This sort of experiment here. One thing that you could technically do. So you can't. You rightfully mentioned because of the temporal aspect. You can't really do this on humans because later relations will change depending on the previous ones, as you mentioned. You can though actually do this on like AI. So I've done this on AI because assuming that they don't update themselves, so you do have to like make a new one each time, so it doesn't remember its previous answer. But assume that you can fix a state of it, and you can just you technically can avoid that, and you can just sort of force this robot to answer your dumb questions about how angry is X compared to Y. But at least that assumption will be okay.
That's sort of
Oh shit! Sorry.
a little circular in the sense that these AI agents are also trained on
That's true.
Experience of certain like seeing tokens in order together.
That's true.
In a certain order tends to have certain relations on that, which gives it because it's a conjunction, which is symmetric. So you end up, I don't know, but it's an interesting idea that you basically taken the time element out of it by taking the expected value of all of them, all the different possible orders you could say
in general, I think definitely I like the idea of considering non-symmetric enriching categories for that. Because I didn't consider that actually. I do wonder, like, because this temporal aspect, I don't know enough category theory, let's just say, to know how to model this, like this time dimension? Do you have any ideas, at least, how to model?
Yeah, so
Like an evolving category.
you've considered a enrichment in a partial order. With this addition.
Yeah.
It's a commutative addition. There's a nice construction such a thing is called a quantale, if it has this addition, not necessarily. So there's a construction which if you take any monoid, for example, a free monoid like lists of some or words in some alphabet, then you take functions on that valued in any quantale, you can get a new quantale out of it by an operation called deconvolution. But it's if you map into truth so that you're looking subsets of your monoid, then it's the setwise product. That's the point. It's a generalization of setwise product. If your monoid is non-commutative, that's going to be non-commutative, even if your underlying quantale is commutative. So you could take any of the V's that you already have and buff them up into one that's non-commutative by giving yourself a monoid, say, of like, imagine the elements that generate it are the things you show to subjects. And then a word is a sequence of things you show to subjects. And most of these tests are done as sequences of things you show to subjects, which are perhaps dependent on the answers to the previous one, but if they're not, it's a monoid. And so you would then have to say that for every two things, you get a function that takes any possible sequence and gives you a number. And that's a closer match to what you actually measure. Because what you measure is I give a subject a sequence of experiences, and then I deduce from that a quantity. So that's a thought.
Cool. Thank you.
Okay. If there are any further questions, we might have to take them downstairs. I think we should probably end the recording